in the semester, we started talking about the force due to gravity. And we talked about the force due to gravity being equal to the mass times the gravitational field strength. Here we're going to expand that equation in order to deal with the force due to gravity due to objects other than the Earth. So let me go through and define the terms in our new equation for the force due to gravity. The capital G here is the universal gravitation constant. So G is going to be equal to 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. And notice the word universal. G is always the exact same value, and big G is not the same as little g. Little m in this case is going to be the mass experiencing the force. So this would be the same as the mass that you would be summing the forces on. Big M is the mass exerting the force. So in our prior examples, we would have been using the mass of the Earth because we were finding the gravitational field strength from the Earth. And R in this case is going to be the distance from center to center of the two objects. We do have to be careful with the distance between center to center. If we have an object like the Earth that is large and there is a satellite in orbit around it, you may in a problem be given the altitude. And this is the distance from the surface to the object. In order to establish the distance from center to center, from the surface of the object is not center to center, because remember, the Earth is a sphere, so the center would be down here. So we would have to take the radius of the planet plus the altitude to get center to center. Now keep in mind, with satellites, we're assuming they're small enough that we can ignore that small distance to their center. So we're really more worried about the ginormous planet because the radius of a planet is pretty big, and that's going to make a big difference in our calculations. The other distance you might be given is if we have, say, Mars, and Mars has a moon called Phobos. So Phobos is going to be in orbit around Mars. You'll be given the orbital radius. And orbital radius already includes center to center, so I should really draw this like this. So whenever you have an orbital radius, you don't need to add in the radius of the two objects into the distance from center to center because it's already center to center. Alright, so now we're going to talk about what happens if you have more than two objects in the system. That means we need to sum forces. So let's find the net force on asteroid 1 due to asteroid 2 and asteroid 3. So force net 1 is going to equal the force from asteroid 2 plus the force from asteroid 3. Now we have to remember gravitational forces are attractive, which means that we need to do everything from the perspective of asteroid 1. So asteroid 2 is going to pull it this way, so that means that that force is positive. Asteroid 3 is going to pull it in the positive x direction as well, so this force is also positive. So you do need to do a check. How would the asteroid pull? If there had been another asteroid over here, it would pull asteroid 1 in this direction, and that force would be negative. Alright, so let's sub in our new equation for the force due to gravity. So the large m in this case would be asteroid 2, and the little m in this case would be asteroid 1. And we're going to divide by the distance between them squared. For our second term, the large mass would be asteroid 3, and the small mass would be asteroid 1. And then we're going to divide by the distance between them, and we have to be careful here, we have to get the full distance between them squared. So notice that when we're looking at this, the big M is always different, and the little m is always what we're summing the forces on. So this number should match this number, should match this number, but these should never be 1, this should never be 1, and they need to be different between the two terms. And be careful that you're getting the full distance. So between asteroid 1 and 2, that's just R1, 2. But to get from asteroid 1 to asteroid 3, you have to add this distance and this distance together to get the full distance between 1 and 3. Now we do have to remember that force is a vector. On the previous slide, all of the masses were along the x-axis. So we could either add them or subtract them, but that's all the direction we have to worry about. But if we have a situation like I've drawn here, where if we're trying to sum the forces on asteroid 1, asteroid 2's force is going to be along the y-axis, and asteroid 3's force is going to be along the x-axis. We can't simply add them together. So we would have to sum our forces in the y direction. So force net on asteroid 1 in the y direction would be the force due to asteroid 2. And the force net on 1 in the x direction would be due to the third asteroid. And once we had our x term and our y term, you would have to do Pythagorean's theorem and inverse tangent to find magnitude and direction. So we do have to remember that force is a vector. The last thing I want to explain here is how to find the gravitational field strength, or G. So we learned how to calculate the force due to gravity earlier in the semester by taking mass times the gravitational field strength. We learned in this unit that gravitational force can be found by taking the gravitational constant times the mass exerting divided by the mass experiencing, or times the mass experiencing, divided by the distance between them squared. I'm now going to equate them. And we'll notice here that the little m's cancel out. So the mass experiencing the force is going to cancel out. And so I can rewrite this as saying the gravitational field strength is equal to the gravitational constant times the mass exerting the force divided by the distance squared. So this allows you to find the gravitational field strength due to a large body. So if you plugged in the mass of the Earth and the radius of the Earth, you would find that the answer gets pretty close to 9.8 that we've been using all semester. So this allows you to see that the 9.8 is actually not a constant value because it depends upon the planet you're on and the distance above the surface that you are on that planet.